Greetings, physicists. Here we're going to talk all about solving force problems that involve inclined planes. So we'll start with the first one. Here's a multiple choice. Got a mountain biker climbing. I mean, he's obviously climbing on his bike. This 20-degree slope. He is not accelerating. And we have his weight. And they're going to ask us some questions about the magnitude of the force on the bike from the surface. So let's draw this. And let's actually use the pen tool to draw this. So there we go. He's on a 20-degree incline. Here's the bike. And there that's his butt. Okay. There's his legs. Okay. Sitting on the bike. And going up at constant velocity. And we're curious about the normal. We're curious about this force here. So let's draw him as a free body diagram where the normal is going this way, the mg is down, and did they say there's friction? Actually, friction wouldn't be up, it would be backwards. Even if there's not, it doesn't matter. This is enough. So, with incline problems, as long as you're moving parallel to the incline, which this mountain biker is, I always encourage you to rotate the incline until it looks like he's moving horizontally. And in this case, that means rotating the incline 20 degrees counterclockwise. So when I'm done with the rotation, I will have the normal up. I will have the mg this way, and I will have, and that's it. And so now everything lines up with the xy plane. So now the normal is with the y plane, we just need to line up the mg. So the mg will have these two component vectors. And because the mg is the hypotenuse, we really don't have to solve this any further. I mean, we know that if this is the angle that it rotated through the 20 degrees, that this vertical is going to be mg cosine, because that's an adjacent angle, cosine of 20. But basically you just have to say, here's the hypotenuse, that's the mg, and his mg we knew was 800 newtons. So 800 newtons, each of the legs of that triangle have to be less than that. Well, think about it. He's not accelerating up or down, so those two forces have to be equal. So if this leg here is less than 800 newtons and it's equal to the normal, but the normal force has to be less than 800 newtons. And this is going to happen anytime you tilt a surface. If you were riding on a flat surface, or you had something sitting on a flat surface, and it's not going to try and accelerate left or right because gravity doesn't go left or right, so the normal up and the mg down have to balance each other, and as soon as you tilt, you're lessening that normal force. In fact, the more you tilt, the more you lessen that normal force, because think about it, the maximum tilt would be a 90-degree tilt. Well, at that point, there is no normal force. The box just falls straight down because the surface doesn't support it anymore. So, little conceptual problem there, but you'll encounter versions of that, I'm sure. Let's move on. Here we go. Something with numbers. All right, now we're not talking about mountain bikers, we're talking about mountain goats. Apparently, these guys have some pretty high skills when it comes to climbing mountains. They can even go up to 60-degree inclines, which for you and me would almost be like climbing the mountain with our hands instead of with our feet. So they can go up pretty sheer slopes. We're curious about the normal force and the static friction on a mountain goat with this much weight, this much mg. So let's draw that. 60 degrees, that's a pretty steep slope. We'll put our mountain goat on there. Mountain goats have those big curved horns. Alright, and if we draw him as a free body diagram, we know his mg goes straight down. He can't avoid that. Gravity pulls towards the center of the earth. We know the normal is going up this way. And if he were to slide, so we know there's a static friction, which means he's not moving. If he were to try and slide, he would try and slide this way. So the friction must be stopping that motion. So I'm going to draw the friction the exact opposite of the way he would go if he were moving, even though he's not yet. So that's our free body diagram here. And like I said before, we're going to spin that free body diagram. We're going to rotate it, in this case, 60 degrees until he's standing flat, or appears as if he's standing flat. And then my new free body diagram will have the normal straight up, we'll have the friction straight left, and this mg, which used to be here, used to be vertical, has now rotated all the way to here, and there's that 60-degree angle. So when I split my mg, so that's my free body diagram. If I were to split that mg, I probably rotated it too much. It looks almost as if I've rotated it flat, but hopefully you can imagine differently. So the normal will be up, friction will be left, and when I split it, I have this horizontal and this vertical, and the vertical is the cosine in this case because it's adjacent to this angle, and the horizontal is opposite. So if I go down here, that is mg cosine theta, and if I go to the right, that is the mg sine theta. This is like in the kinematics chapter where the acceleration down an incline was g sine theta. Well, then the force is mass times acceleration, or m times g sine theta. And that's my free body diagram there. And the go to standing still, he's not only is he not moving, but he definitely is not accelerating. So this vector and this vector have to be equal, and this vector and this vector have to be equal. So let's write those as equations now, as sigma f equations. Sigma f equals ma, but there is no acceleration. So the force of friction has to be equal to mg sine theta, and the normal force has to be equal to mg cosine theta, which is pretty standard stuff for something on an incline. As long as you measure your theta, just warning, as long as that theta is measured from the horizontal. If they give you theta from the vertical, you gotta flip those. All right, what were my numbers? Well, I had 900 newtons. I had the 60 degrees, and I think that's all I need to plug in, other than gravity. So the force of friction will be mg is his weight. So actually I don't need to plug in gravity because the weight is both of those together. So I'm going to replace mg with 900 newtons. All right? And sine theta is sine 60. Here it's going to be 900 newtons cosine 60. And I'm bad. I always forget which one is a half. One of those is a half and one of those is root 3 over 2, but I can absolutely never remember. So I always wind up plugging them both into my calculator. I really should memorize that. Okay, cosine is a half. So the bottom one here is going to be 450 newtons of normal force, which means the other one is root 3 over 2, but I'm not going to be able to do that in my head, so I'll just put it in the calculator. So the sine version is 780 newtons of force. And I'm rounding to 2 sig figs, which seems appropriate here. Although if I rounded to 3, I think it's the same thing. Okay, there we go. So, static incline problem. Let's move forward here. Here's a moving one. 23 kilogram child going down a straight slide at 38 degrees above the horizontal. And we know that there is friction on this slide, so they first ask us to draw a free body diagram. Whoops. So I can do that without numbers. So the child, so let's, I know it says draw a free body diagram, but I like to draw the slide as well, just for me. It's a steep slide. Poor kid. There's a slide. And here's the child. All right. So, what's the free body diagram for him? Free body diagram for him looks like this. He has a normal force that pushes him off of the slide. He has an mg that goes straight down. And the frictional force, which is 90 degrees to the normal force and points backwards of his motion, or 180 degrees from his motion. That's my free body diagram. Don't split anything, don't rotate yet. This is the free body diagram. Anything you do after this is the analysis section. Okay, next, how large is the normal force on the child? Well, it doesn't ask me for friction. Good, I'm not going to have to deal with that. So the normal force, if I rotate this, remember this is a 38-degree slide. If I rotate this 38 degrees, I will have friction this way. I will have normal up. I will have an mg out to here somewhere. And since I'm only looking for the normal, I'm only going to bother with this guy here. And there's my 38-degree angle. So the downward force there, I know I didn't drop proportionally. Bad me. But the normal force there and this force here should be equal because he's not like leaving the surface of the slide. If he bounced off of the slide, we would have to have a difference there. All right, so we'll say the normal force is equal to, well, that's the mg, and this is an adjacent leg, so that would be mg cosine theta. Or his mg, did they give me the mass of this child? They do, 23 kilograms. All right. So he's a 23 kilogram child, and g is 9.8 meter per second squared. And cosine of 38 is 1/2. I do remember it from the last problem. Sweet. If you want to estimate this really quick, 9.8 is about 10. 10 times 23 is 230, and half of 230 is 115. So your answer is going to be very close to 115. It might even round to that. But I'll go ahead and do the whole thing so you can see it. So 23 times 9.8 times 1/2. Yep. So the actual answer is like 112.7, which if you round to 3 sig figs is 113. And these are newtons. Kilogram, meter per second squared. So yeah, 115 would have been a nice rough estimate. And if you ever see on a test, I don't know if it said it on this particular problem, I don't think it did. No, this one says how large is the normal force. If you ever see in a test something that says about how large is the normal force, or the normal force in the child is roughly, if you see words that suggest something like that, that means you can approximate gravity as 10. That's asking you to estimate. So anytime you have to estimate gravity, it's 10 meter per second squared. Pro tip. Last one. All right, we got a dump truck. We've had a dump truck problem before. Here's another one, which got the steel bed. The bottom of the dump truck is steel, or the bed, and the thing it's holding is steel. Key right there. The bed of the truck is raised until that truck begins to slide. What is its acceleration? This is a bear of a problem. Because look through there. There is not a number at all written in this problem, but they want a numerical answer. So you go, where are my givens? Okay. Well, the first clue is that they give you the names of the materials. Now, old steel is not important here. It's steel on steel. I don't think anybody at this level of physics is going to make a difference between old steel and brand new steel, as long as it's not like lubricated or something. So if we go back and Google steel on steel, or if you look back to the other problem where we did this before, we can find a coefficient of friction. Now, I'm actually going to have to find 2 of them. That's the tricky part of this, is that this problem requires 2 coefficients of friction. Now, I know there's a page in the book that has these, but you can also just Google it online, and you should get the same values. So here it is, steel on steel, static is 0.8, kinetic is 0.6. So the coefficient of static friction is 0.8, and the coefficient of kinetic friction, this is just for steel on steel, 0.6. Now, the reason I say we're going to need both has to do with the fact that I'm slowly lowering the bed of that dump truck. So the truck is like this, right? Here's the truck. And I'm increasing that angle theta until this trough starts to slide. Well, what's going to happen is, until I get to that angle theta, it stays in place. And while it stays in place, it's using this static coefficient of friction. And so we are going to get to that perfect theta where we're just barely cause it to slide, where it just overcomes static friction. But look what happens when it overcomes static friction and starts to slide. The coefficient of friction gets smaller. And now we're not going to be in equilibrium anymore, and we will now be beating the coefficient of static friction. And so it will accelerate. That's why it asks for the acceleration of the trough. Whew. Really a doozy, if you didn't recognize that. So let's do it this way. We need to find the perfect angle where the mu static just fails. So the maximum force we could get out of a 0.8 mu static. So let's go ahead and draw a free body diagram for this object as we tilt it. So at some angle theta, it will have a normal force going this way, we'll have a frictional force going this way, and an mg going down. And we'll have that angle theta. So let's rotate this theta degrees to make it easier to analyze. Normal up, force of friction left, mg this way, and this is our new angle theta. So now that I'm splitting things, the downward is the cosine because it's adjacent, and the rightward is the sine. So I'll have mg cosine theta and mg sine theta. And so I can do my two equations again. I can make my horizontal equation and my vertical equation. So my horizontal equation is going to be this force and this force competing with each other. I'll make down the incline positive. So mg sine theta minus the force of friction has to equal ma. Now before it starts moving, that a is 0. So the mg sine theta will just be equal to force of friction. And then we have the vertical, which is these two forces. And so I've got the normal up, I'll say is positive, minus mg cosine theta has to equal the vertical mass times acceleration. But again, that's 0 so far. And so when I set those two things equal to each other, what we will see, I'm going to solve for force of friction, I'm going to solve for normal. Yeah, I think that works, okay. So we know mg sine theta will be equal to force of friction. We know normal will be equal to mg cosine theta. And because this is a friction problem, we also have that the force of friction, look at that F, that the force of friction is equal to mu times the normal. So let's sub in for that. Let's substitute both. Let's say that the force of friction, which we said was mg sine theta, will equal mu times mg cosine theta. Okay? And look at that, mg cancels. And if I divide by cosine theta, let's get rid of that and divide it over to this side, I get tangent theta. So mu is tangent of theta. Now this is still my mu static. This is before the thing has started working. So what this means is that these forces will be balanced up to a maximum angle of tan theta, or a maximum angle of theta where tan theta equals mu static. So let's plug in what I know for mu static. Mu static is 0.8. So tan theta has to equal 0.8, or tan minus 1 of 0.8 has to equal theta. And again, make sure you're in degrees. I think the first time I did this problem I had it in radians. So tan 0.8, and oh no, I did it wrong. I did tan minus 1. Tan minus 1 of 0.8. There we go. 39. 39 degrees is my theta. So I will tilt the dump truck to 39 degrees. The thing will start moving, and then this 0.8 will not be 0.8 anymore, because a kinetic coefficient of friction is always lower. In fact, it's going to go to 0.6, which will change my equations. If I go back up here, once this thing is moving down the incline, this frictional force gets smaller. So if my if I redraw my free body diagram, the normal up did not get smaller at 38. And the portion of gravity down, the mg cosine theta, did not get smaller. So those two things should still be equal. That's not going to change. But think about it. Forward, what's pulling me down the incline? Mg sine theta is pulling me down the incline. But what's pulling me backward? The friction force. And when I make mu smaller, because it's moving now, look at that. That arrow becomes smaller. And now those forces are not balanced, which is why this thing is going to accelerate down the incline. So I need to rewrite my sigma f expression in the horizontal direction. So here we go. We're going to have, again, I'm going to make down the incline to be the positive. So mg sine theta minus the force of friction, give myself some room, equal to ma, but a is no longer 0. A will now be positive because those arrows don't cancel each other out anymore. Now my vertical is still the same. The normal is still equal to the mg cosine theta because the object does not accelerate through the floor, right? It doesn't accelerate relative to the surface. It stays stuck to the surface. So I can still use this. And this is still true, that the force of friction is still equal to mu times the normal, only now it's a mu kinetic because the thing is moving. So when I go to plug into that coefficient of friction formula, mu kinetic times the normal, well, the normal is still mg cosine theta, but the force of friction now has changed, and now I have to solve for the force of friction. It looks like it's going to be mg sine theta minus ma. There we are. So that's the equation now that I have to end up solving. Well, look at this. Even though we did all that change, there is an m term in, or there is an m factor in every single term. So if I divide both sides by m, the m's will still go away. So it still does not matter how heavy this water trough is. That's fun. What I'm looking for is a. I want to isolate a. So I'm going to add it to the other side because right now it's negative. So I'll get g sine theta equal to a plus kinetic mu times g cosine theta. And then I will subtract this. And so I will get g sine theta minus mu kg cosine theta equal to a. And we figured out the angle. That was what we did last time. We now know the angle is 39 degrees. So let's plug all that in. So g is 9.8. And then I need the sine of 39. So let's do sine of 39. And I'm going to get 0.625 minus the new mu k is 0.60 times 9.8. I'm not putting units in right now, but notice that g is in meter per second squared. Mu does not have units, sine does not have units, so we will get everything in meter per second squared. So the last thing I need is cosine of 39. And I will get 0.78. All right, all of that together. So this is a lot to keep carrying here. Here we go. 9.8 times 0.675. 625 actually. Is 6.125 subtract 0.6 times 9.8 times 0.78. That's 4.5864. And when I subtract them, I get 1.54. Can I be that precise? What are my sig figs in this problem? Too many pictures. There are no sig figs in this problem. I guess I had to look up these values, and those are both to 2 sig figs, so I'm going to be at 2 sig figs in this problem. Here we go. So I'm really going to round this to this digit. So 1.5, and it was an acceleration, so it's meters per second squared. So this thing will accelerate off the end of the dump truck at 1.5 meters per second squared. Tough. That's a level 3 problem for sure. So, hope this was useful to you in understanding how to solve incline problems.